Every year, the University of Kentucky participates in the ASABE International Quarter Scale Tractor Student Design Competition. The competition allows for small teams of engineers across the country to design and build a small quarter scale pulling tractor. So the way that the University of Kentucky's team is organized is they assign smaller groups to work on individual parts of the tractor. So this senior design team was assigned the clutch drivetrain assembly. The clutch is an essential part of a tractor because it allows engagement and disengagement of power from the engine to the drivetrain. So several performance events at the competition every year require lots of starting and stopping and rough type of handling of the tractor because they're pulling like large sleds and maneuvering through sand and speed bumps and all kinds of things like that. So obviously a reliable clutch operation is key to maintaining operator comfort, maximizing performance, and operation of a safe vehicle.
The previous clutch design used an electromagnetic and a centrifugal clutch. The centrifugal clutch was used to smoothly start the tractor off from a stop, and then the electromagnetic clutch was then engaged to ensure that there would be no slippage during pulling. The sprag clutch, which works the same way as a ratchet, ensured that the electromagnetic clutch would be engaged rather than the centrifugal clutch. The issue with this system was that there was only a 1-to-1 gear ratio available. In previous years, there had been a continuously variable transmission used, and this would basically allow infinite gear ratios, which would help during certain pulling events so that you could change gears on the fly rather than having to shift in the transaxle and you would have to stop, which would waste time and negate any extra points that you earned by switching gears.
The proposed solution consists of 3 electromagnetical clutches with identical primary pulleys and varying secondary pulleys. So the ability to change gears without stopping was desired in the new design so that the driver could shift on the fly, therefore avoiding the need to stop during a timed event and also providing the torque needed. So in case the driver accidentally shifts into the wrong gear or the wrong gear is chosen, they can just switch quickly without having to turn the tractor off and back on again. Our proposed solution will reduce the number of unique parts on the tractor because we use a common clutch component rather than 2 different mechanisms. So only using electromagnetical clutches requires a new mechanism for engaging and disengaging each clutch to smoothly transfer power. The proposed solution will also allow for a clutch pedal to be used as the primary mechanism for disengaging the clutches, which will provide a more intuitive method and improve safety. We will also have 2 push buttons on the tractor that can also be used to shift through the clutches.
So our final design, as you can see in this rendering, is a 3-stage electromagnetic clutch system. The 3 clutches are mounted in parallel, and there are 2 sprag hubs that we machined out of aluminum, and these help to make sure that the fastest gear ratio will be engaged to the driveline. All of the pulleys have been modified so that they bolt up correctly to the clutches and to the sprag hubs. And there are 3 belt tensioners to keep friction between the pulleys and the belts so the power can be transmitted. Also, each of these tensioners have markings so that they can be set to the same tension to ensure that power will be transmitted the same way through each belt. Another highlight of this design is that if one of the belts fails, the lower ratio clutches will still be engaged so that the power will still be transferred and there won't be any unintentional stopping or loss of points during the competition. And Thomas will be talking more about how we achieve smooth clutch engagement without the use of the centrifugal clutch.
Okay, so now we'll move on to the controller development section of the project. So initially what we did was we connected a electromagnetic clutch, or the electromechanical clutch that we were using, to an Ogira soft start controller, which basically simulates the effect that a soft start shifter would give you. So essentially reducing the amount of like jerk or resistance that you get when you try to shift. So this is essentially implemented to try and maintain a smooth ride throughout the shifting experience, whether you're starting up the tractor for the first time or shifting up or down through the gears. So when we did that, we were able to collect this data plot from an oscilloscope, and it gave us a duty cycle of right around 40.9% specifically, so around 40%, throughout like about a 1 to 2 second window. So basically what we're trying to do is simulate that same waveform without actually using the soft start relay. So in order for us to actually simulate the Ogura soft start relay, what we decided to do was use an Arduino along with Arduino code to modulate the duty cycle of each clutch depending on which one is engaged. So in order to do that, what we have to do is we have to constantly check for button inputs, whether that's a new upshift or a new downshift, or you changing the potentiometer, or essentially you feathering the clutch, which will then alter the duty cycle that's sent to the currently engaged clutch. So in order for us to do that, we are constantly checking for the gear shift value, right? Which is essentially what state the system is in, whether it's in first gear, second gear, third gear, or vice versa. And in order to do that, it takes the up buttons and down buttons and keeps track of those shifts. So if you go from first to second gear, it will say, okay, the previous button was in button state 1, the new one is button state 2, therefore we're going from first to second gear, and so on and so forth. Now, in order to modulate the duty cycle, or essentially make sure that we're getting a soft start like the Ogura was doing, what we'll do is we'll send an initial duty cycle of right around 100 or right around 40.9%, which is what we saw in the oscilloscope graph, and then delay the system for about 1 second, 1.5 seconds. This is one aspect that we were not able to test, and then send a full duty cycle of 100% up to that engaged clutch. That way we get some slipping of the electromagnetic disks when we're setting that duty cycle right around 40.9%. And so that should simulate a soft start or a smooth shift. So in terms of our final product, we weren't able to actually assemble the completed design due to the fact that we didn't have any access to the dynamometer in the shop, which would actually allow us to run loads through the system, which essentially is testing our shifting mechanism. So instead, what we are able to do was create a testing procedure, which is essentially just the procedure for making sure that we are implementing that increased duty cycle for each soft start properly. In addition, we have also tested completely our controller, so we know that we're getting valid inputs from the up buttons and the down buttons, and as well as the potentiometer. So overall, the only things that we really needed to do leading up into spring break, right before we were not able to work anymore, was essentially finish the code, which has now been done, and then test that code on the implemented built system. So with that said, I think everyone in our group, I can speak for all of us, we're very happy with how everything ended up. However, it would have been nice to actually assemble our clutch system and see it working. Appreciate you all.